So now we're going to look at a discussion of ions and how they behave in an aqueous solution. All right. So we talked about ions before, and of course you should know by now that ions are basically species that carry a charge, and that charge can be either negative or positive. Positive ions are known as cations, and negative ions are known as anions. All right. So we're going to look at basically what happens when these compounds that contain ions, when they're in an aqueous solution, how they behave, what they do, and so on. So the first thing we're going to talk about is the electrical properties of such solutions. All right. Now, in solutions, we can have two types of charges. Ions, they can be positive or negative, as we said before. And what this diagram is showing you is basically how ions behave or how charges behave with respect to each other. So this is, of course, purely hypothetical, but it basically relates to what actually happens in the real world. So what we have here are basically different particles of different types of charges. This one here, this pair here, they have no charges, and therefore, as a result, there's no attractive force between them or repulsive forces. On the other hand, in this case here, we have a positive charge in close proximity to a negative charge, so therefore there will be an attractive force that exists between them. And then over here and here, you have situations where we have particles with like charges in close proximity to each other. And what will happen in each of these cases is that you're going to have repulsion. So that happens between the two plus charges here and the two negative charges here. All right? And this is essentially how charges behave in an aqueous solution when these charges are found on ions. All right? And as stated down here, the behavior of the charges is kind of similar to the behavior of simple bar magnets. As you know, bar magnets basically have two poles. You have the north and the south pole. And if you try to bring like poles, like two south poles together or two north poles together, what you'll find is that there'll be a repulsive force between those poles. However, if you bring a north and south pole close to each other, then there'll be an attractive force. All right? So it's very similar. The magnetic forces that exist between bar magnets is very similar to the electrical forces that exist between charges. Now, one of the properties of ions is that when, or ionic compounds, I should say, is that when they are dissolved in water, or if you melt it and it becomes a liquid, we call that a molten form of the compound. What will happen is that the ions will start moving around freely, right? So you're going to have the positive ions, which are the cations, and the negative ions, which are the anions, moving around freely in either the solution or the molten form. So that's what's being demonstrated here. Now, if you try to pass an electric current through it, you will succeed. And the reason why is because in order for an electric current to pass through anything, you must have mobile charges. Now, in the case of the external circuit in this setup here, where you have the wires connected to the electricity source, those charges will be electrons. Electrons will be running through the wires, and that's how we have electricity being conducted in the external part of the circuit right here. However, here, where you have the ionic compound in either the aqueous solution form or molten form, what you'll find is that the ions will move within that medium, and therefore the electric current will pass through it. And in this particular case, let me just describe what's happening here. So we have the electricity source, and there are two signs or poles of the electricity source. You have the positive and the negative, and therefore this positive electricity source is connected to this piece of metal. So therefore this would be positive as well. We call this the anode. And this part, which is connected to the negative end of the electricity source, is also negatively charged, and this is called the cathode, right? So what's going to happen is that the negative ions will be attracted to the positive electrode, the anode, and the positive ions will be attracted to the negative electrode, which is the cathode. And that's the reason why the negative ions are called anions, because they're attracted to the anode, and the positive ions are called cations because they are attracted to the cathode. So therefore, as a result, throughout this whole system, you're going to have an electric current flowing through it, all right? So that's one particular important property that is displayed by ionic compounds, and that is that when you dissolve it in water or if you melt it to the liquid state, then it will be able to conduct electricity. Please note that this will not happen if the ionic compound is in a solid state. When it's in a solid state, it will not conduct electricity unless it's in an aqueous solution or molten. All right. So that's basically what is happening in this case. So this is just rehashing some things I said before. So let me skip to this. Now, what we're going to talk about are different types of solutions, aqueous solutions, right? And the first category of aqueous solutions we're going to talk about are what we call non-electrolyte solutions. And these are solutions of compounds which will not form ions in an aqueous solution and therefore, as a result, will not conduct electricity. So one example of this here is this solution here of a 1 molar methanol solution, all right? Methanol is not an ionic compound, and therefore, when you add it to water, it will not form ions, all right? So as a result, if you try to pass an electric current through it, you will not succeed. There'll be no electric current passing through, and that is demonstrated in this setup here. So in this setup, you have your methanol in this beaker right here. You have your two electrodes, one is a cathode and one is the anode, and you have, as a part of the electrical circuit, you have a light bulb right here. So if an electric current would pass through here, this would light up, but that's not the case here because methanol does not allow an electric current to pass through. So therefore, we call solutions such as solutions of methanol electrolytic, or I should say non-electrolytic solutions, all right? So that's basically what happens in that case. Now, let's look at this case where we talk about a strong electrolyte. Now, the example that is shown here is a solution of 1 molar sodium chloride. Sodium chloride is ionic and when dissolved in water produces ions, as you can see here. So when you try to pass an electric current through it, then guess what? The light bulb will light up, and therefore we know that sodium chloride is an electrolyte. And in particular, sodium chloride is said to be a strong electrolyte, right? And the reason why we consider it to be a strong electrolyte is that it conducts electricity very well. And the reason why it does so is because when you add sodium chloride to water, all the sodium chloride will be forming ions. So therefore, the amount of ions present will be relatively high, and therefore it will easily allow an electric current to pass through it. Now, we have another category of electrolytes known as weak electrolytes. And weak electrolytes, as the term suggests, do not conduct electricity as well as strong electrolytes. Now, they do conduct electricity, but it doesn't do so to the same extent as something like sodium chloride. And that is demonstrated in this setup right here. Now, the solution that we're looking at here is a solution of acetic acid. Acetic acid is an acid which is a weak electrolyte, and that's because when you add acetic acid to water, not all of the acid molecules will be converted to ions, all right? So basically, for the same molarity of each of these solutions, the acetic acid will have fewer ions, and therefore, because it has fewer ions in the aqueous solution, it does not conduct electricity as well, and that is demonstrated here. As you can see, the light bulb, which is a part of the circuit, it lights up, but not as brightly as in the case of sodium chloride. So therefore, we can conclude, based on this experimental setup and what we observe, we can conclude that acetic acid is a weak acid. Okay, so now that we have covered that, let's talk about ion concentrations in solutions, all right? So basically, this is a symbolism that is used in chemistry, which basically represents that the concentration of whatever is within here. So for example, if I were to write this down, the concentration, if I were to write this down, where we have NaCl within square parentheses, then what this is saying is that the concentration of sodium chloride is equal to 0.1 m, all right? So that's what the square parentheses mean. Okay, so for a solution that is 0.01 m sodium chloride, what you'll find is that sodium chloride will undergo complete dissociation to form Na plus and Cl minus ions, right? And I use the term dissociation. Dissociation is basically a fancy word we use in chemistry to say that something splits up into different parts, right? So in this case here, sodium chloride basically splits up to form sodium ions and chloride ions when you dissolve it in water. And therefore, based on what we see here, we can conclude that the concentration of sodium ions is 0.010 m, and the concentration of chloride ions is 0.01 m as well, right? And that's because there's a 1 to 1 to 1 ratio between the sodium chloride that you start off with, the sodium ions that you end up with, and the chloride ions that you end up with, all right? So that's basically what happens when you dissolve ionic compounds in water. It splits up to form the different ions that makes up the particular compound, all right? Now, if you understood what I mentioned or talked about with respect to strong and weak electrolytes, then this concept will be relatively easy for you to understand, and that is the concept of strong and weak acids. However, before we talk about strong and weak acids, let me define exactly what an acid is. An acid is basically a substance which, when dissolved in water, produces hydrogen ions, all right? So just to give a couple of examples of this, let me go to my writing pad right here. Let me clear this here. So there's an acid known as hydrochloric acid, and this is the formula here. And basically, when that dissociates, it forms H plus and Cl minus, right? So by virtue of the fact that it forms H plus, that means that this is an acidic compound, or it's an acid, all right? Here's another example, HNO3. When this dissociates, it forms H plus aqueous and NO3 minus aqueous. So basically, this is what all acids have in common. They dissociate to form hydrogen ions. Now, they will form some other negatively charged ion, but the main thing that makes this an acid and this an acid is the fact that when they dissolve in water, they produce hydrogen ions, all right? So let me go back to the PowerPoint here and continue our discussion. So now we're going to make the distinction between two types of acids. We have weak acids, which are acids which undergo partial ionization or dissociation, right? In other words, only a small fraction of the molecules will be converted to ions. And then we have strong acids that undergo complete dissociation, all right? And therefore, as a result, strong acids are very good conductors of electricity, while weak acids are very weak conductors of electricity, all right? Now, going back to this, to the discussion about the weak acids, we can represent the dissociation of weak acids by using a double arrow. And what that indicates is, and I'm going to use acetic acid as an example right here. So we use this double arrow here. Basically what that indicates is that there's a back and forth taking place. So what do I mean? I mean that the acetic acid will undergo dissociation to form these ions, but at the same time, these ions will recombine to form acetic acid. So as a result, the concentration of H plus in those solutions would be relatively low, and therefore acetic acid is considered to be a weak acid for that reason. Acetic acid is one of several organic acids which are typically weak acids. So if you were to encounter any other organic acids, more than likely those acids would be weak acids, right? And this is just showing you a ball and stick representation of the dissociation. So this is basically representing the same thing as written here in this equation. Okay, so how do we recognize strong and weak acids? Well, conventionally speaking, and this is not even true in all cases, but in most cases I would say, whenever you look in any chemistry textbook and they write down the formula for a strong acid, they usually put the hydrogen first, so like this or this. And then in the case of weak acids, they usually put the hydrogen that is leaving upon ionization at the end, all right? So that's conventionally what is typically done in most textbooks, right? However, I would strongly suggest that you memorize these 6 acids as strong acids, all right? So we have hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric acids. These are all these are all strong acids, all right? So if you memorize these acids as strong acids, pretty much all other acids that you're going to encounter will be considered to be weak acids, all right? Okay, then we have strong and weak bases, and the same concept applies, but I need to define what a base is, and I forgot to include that in this PowerPoint, so I'm going to write it up here. Oops. Okay, so a base is a substance that produces hydroxide ions in an aqueous solution. Aqueous solution. All right? So that's what a base is. A base produces hydroxide ions. So a base is considered to be the chemical opposite of an acid, right? So strong bases. We have strong and weak bases that fall under the general category of bases. Strong bases basically are very good conductors of electricity because they undergo complete ionization in water. So an example of a strong base would be sodium hydroxide, because when that dissociates in water, it forms Na plus and OH minus. All right. On the other hand, weak bases, they undergo partial dissociation, right? And they tend to be molecular compounds. They tend not to be ionic. A good example of this would be ammonia, right? Ammonia is an example of a weak base. Now, the way ammonia behaves like a weak base, let me do that, squeeze that down here, is that when you add ammonia to water, this is what happens. It forms NH4 plus aqueous plus OH minus aqueous. All right? So again, the hydroxide ion is formed, but you'll notice I've used the double arrow here going in opposite directions to indicate that the reaction is going back and forth, and therefore as a result the concentration of hydroxide ion here would be lower than you would expect, especially compared to strong bases like sodium hydroxide. Okay, so this begs the question, how can we tell the difference between a strong base and a weak base? Basically, these compounds listed here are considered to be strong bases, right? And pretty much all other bases would be considered weak for our purposes, all right? And you'll notice that these are all hydroxides of groups 1A and 2A. So this is an easier list to memorize. Okay, so that's it as far as strong acid, weak acid, strong base, weak bases, and strong electrolytes, weak electrolytes. Okay, so now I want to talk about a reaction between an acid and a base, which is known as a neutralization reaction, right? So as stated here, neutralization is a process of the reaction between an acid and a base canceling out each other. So basically, the basis of this particular understanding of this reaction is that acids are acidic, bases are basic, but when they react, they produce products which are neither acidic or basic, and they're neutral. And as stated here, the products of this neutralization are two of them. One of them is water, and the other is what we call a salt. And the formula for the salt is based on the formula of the acid and the base that is undergoing the reaction. So here is a simple example. Hydrochloric acid, that's what this is, right? When this is reacting with potassium hydroxide, then you're going to end up with water, as we said before, and this compound, which is known as potassium chloride, all right? And if you examine the formula for potassium chloride carefully, you'll see that the potassium here, I'm going to put potassium in a box here, comes from the potassium in the base, right? And the chloride here, I'm going to put that in a circle, comes from the chlorine in the acid, all right? So therefore, basically, it is the chloride from the acid coming together with the potassium from the base to form potassium chloride. And therefore, the hydrogen, let me use a different color here. I'm going to use red. The hydrogen and the hydroxide here will come together to form the water, right? So that's basically how the neutralization reaction works, all right? Okay, so let's talk about, should I talk about this? Okay, let me go into this right here. Yes, let me talk about this. So let's talk about what we call the net ionic equations, right? Now, this is important because it actually shows what is going to happen in terms of the species reacting with each other, and basically any other species that does not involve themselves in the basic underlying reaction, we call them spectator ions, right? So as stated here, species that remain unchanged on both sides of the chemical equation are said to be spectator ions. Okay, so we're going to use the same reaction that we saw before, the reaction between hydrochloric acid and potassium hydroxide to form water and potassium chloride, all right? Now, this here, we call this, for the purposes of determining the net ionic equation, we call this the molecular equation. Now, to be perfectly honest, this is a bit of a misnomer because not all the species involved here are molecular. But that's a term that you'll see in textbooks when it comes to describing this equation here. Now, what we need to do in order to get the net ionic equation is that we need to examine each of these species to see if they will undergo complete dissociation in water, right? So in the case of the hydrochloric acid, if you remember, we said that that's a strong acid. So that will undergo complete dissociation. So this will form ions, right? The same is true for the potassium hydroxide. The same will be true for the potassium chloride. And the reason why is because any ionic compound that is in an aqueous solution will undergo complete dissociation. On the other hand, water, being a molecular compound, will not undergo complete dissociation. So we can represent the changes that will take place by writing down this equation right here. And this equation is called the ionic equation. And what this shows you basically are those species that will exist in ions or as ions in an aqueous solution as a result of dissociation. So as we said before, hydrochloric acid is a strong acid, so it will dissociate completely to form H plus and Cl minus. Potassium hydroxide is a strong base, so it will undergo complete dissociation to form K plus and OH minus. Water is not ionic and not a strong acid, not a strong base, so therefore it will not undergo dissociation, so we simply leave it as it is. Potassium chloride is an ionic solution in an aqueous, well, an ionic compound in an aqueous solution, so that will undergo complete dissociation to form K plus and Cl minus, all right? Okay, so now that we have determined the ionic equation, remember now the aim is to get the net ionic equation. So to determine the net ionic equation, what we do is to identify the spectator ions. And as we said before, the spectator ions are the species that remain unchanged on both sides of the equation. So if you look at this equation here, you'll notice that the chloride ions exist here on this side and also this side on the right side of the equation. So those are spectator ions. We can cancel them out. And the same is true for the potassiums, right? We have the potassium here, we have the potassium here. So therefore, these are the spectator ions. The chloride ions and the potassium ions are the spectator ions, all right? So therefore, to get the net ionic equation, we just write down what is remaining after the cancellation of the spectator ions. And the final result would be H plus aqueous plus OH minus aqueous to give H2O liquid. And that will be the net ionic equation. Okay, so much for that. The next video, I'm going to be talking about another related topic known as precipitation reactions. All right? Okay, until next time.